Hello, friends. This is a video on the binding energy and mass of deuterium. So first, a little reminder that deuterium is sometimes called heavy hydrogen. What is it? Well, it's a proton attached to a neutron by the strong force. The strong force is holding together, I should say the strong nuclear force or the residual, right? Strong force. The strong nuclear force is holding the two nucleons together. A nucleon is that which makes up a nucleus. It's a proton or a neutron. That's just what a nucleon means. It just means a proton or neutron, that which makes up a nucleus. So this is the nucleus of a deuterium atom. We're just looking at the nuclei. It's the study of the nuclei of atoms is what we're doing here. So the simplest one you can have is a proton. The second simplest one you can have is a proton and a neutron. So remember hydrogen, although technically deuterium is hydrogen, right? Simple hydrogen. Sometimes it's called protium. Or simple hydrogen is 1,1, which is just a proton. So a hydrogen nucleus is a proton. Hydrogen and protons are the same thing in terms of the simplest proton you can have, a simplest atom you can have, hydrogen. Now, deuterium is a form of hydrogen or heavy hydrogen. Because remember that the important number is the number of protons. So a little notation, elemental notation. It should take a moment. Elemental notation is important to review in that we have the element, right? Say we have carbon, right? This is the number of protons. This number is the number that matters. This is what matters. I mean, obviously, protons and neutrons both matter, but what I mean is what matters means that it identifies the element. That's what I mean by matters. Obviously, that can mean many things. What I'm using that word for is it identifies which element we're talking about. So always, if you have 6 here, you have a C here. It's carbon. If you have one proton, you have hydrogen. If you have 2 protons, you have helium. But this can change. I could have 1 neutron and 2 protons. I could have 2 neutrons and 2 protons. I could have 3 neutrons and 2 protons, and those are all helium. So this is, right, 1 neutron and 2 protons. This is 2 protons and 2 neutrons. This is 2 protons and 3 neutrons, right? Kind of see what I'm getting at, right? So the top number is protons plus neutrons. The bottom number is just protons. So this is P plus N. So this is just number of protons. So carbon 12. So when you have a name like element number, right? So helium 4, what does that mean? Well, that means helium, but the 4 means protons plus neutrons. It's total weight, it's total mass. And be careful, it's total mass is protons plus neutrons plus the binding energy or minus the binding energy, however you look at it. That's what I'm going to talk about in a second. But in terms of its like mass number, sometimes this is called mass number. It's just number of nucleons, right? Mass number or number of nucleons. right? So helium-4 means you have 4 total, but helium means you have 2 protons. So the 4 goes here, and helium means 2 goes there. Rewind that if that needs some clarification, but that's it, right? So cool, we got it going on. Now, here's the whole point, right? The mass of a nucleus, and I'm going to write it like this, equals the mass of protons plus the mass of neutrons, right? How do I write that? Number of protons times the mass of a proton. I'm going to write it like this. Equals the number of protons times the mass of a proton plus the number of neutrons times the mass of a neutron plus the binding energy. But the binding energy is negative. And there's a reason I'm writing it as like plus a negative, and that's because I would remind ourselves that binding energy is negative. So when we solve for binding energy, we always want to make sure that it's negative. It's negative because it's an attractive force. That's not that important. You could write minus binding energy, but I'm going to do it like this. This is how I'm going to do it because it's attractive, right? So this is the formula that you're going to use. Really important, right? This is it. So it's easy. So example, deuterium. Sometimes written as this, sometimes you'll see it as a D. That's misleading because you want this to be the element hydrogen. Deuterium is hydrogen. It's heavy hydrogen. So typically, I'm not going to write it like this. I'm going to write it like this. But I'm going to use the word deuterium or heavy hydrogen. It's a hydrogen with an extra neutron. So when a proton and neutron maybe were to come close together, the residual strong force, and notice I'm using my words very carefully, will add energy that then when they clap together, that energy goes into some other form. So when they clap together, the strong force turned potential energy into kinetic energy. The kinetic energy got released, and we ended up with more negative potential energy. So when they're together, after the clap, right? Boom. Some energy was released. I have to be careful. Like you say, energy released, what does that mean? Well, it can be released in the form of light. It can be released in the form of heat, right? We're going to see in this case, we have to be careful. Sometimes it's released in the form of particles, other particles, but we need a process for that. We don't have that. So I'll say light and heat are pretty much the two, right? When you say energy is released, there's no such thing as just energy. What kind of energy? Light energy, heat energy. Hope that makes sense. Light and heat, easy done. Boom. You can start to see why stars start to work. Very bright, very hot. Right? Where does that come from? Right? It comes from actually these little nuclear forces. Strong force doing like a small clap, and that clap releases a little bit of energy. But if you do this countless numbers of times, trillions of times, you're going to get a lot of light and heat coming out of that. Pause. Does that make sense? Isn't that a cool picture? I hope that made sense, right? So, some numbers. So once again, example. Let me clear my picture here. We have the mass of a proton on its own, 1.67262 times 10 to the negative 27 kilograms. Mass of a neutron is 1.67492 times 10 to the negative 27 kilograms. If the binding energy of a proton and a neutron in deuterium is say we get that it's negative 3.564 times 10 to the negative 13 joules. Meaning, you can say here, when they're separated, the potential energy is 0. And when they're connected, the potential energy is negative 3.564 times 10 to the negative 13 joules, which means that amount of energy was released, which means positive 3.564 times 10 to the negative 13 joules was released by bringing them together. That's light and heat coming out. Boom. The point is, but they're together, they're left with a deficit of energy, which manifests in a deficit of mass. So they actually are less heavy, which is remarkable that this energy released actually means that their wave functions vibrate a little slower. They're actually one combined wave function now. Deuterium has like a wave function solution in the Schrodinger equation. It actually doesn't look like two balls. It actually looks like a oblong spheroid, where like the proton and neutron like are everywhere and nowhere. It's kind of crazy. I'm happy we went over that because that actually might make a little more sense if that ever made sense at all. Pause and rewind that, what I said. I hope that made sense. But either way, what I'm focused on are these numbers. So the question is, ooh, let me draw this in a different color. Ooh, here's a good color. So what's the question? What is its mass? What is the new mass? What is the mass of deuterium? Oh, that's easy, right? Because the mass is going to be the number of protons times the mass of a proton plus the number of neutrons times the mass of a neutron plus the binding energy over c squared. I should have emphasized that. I realized I forgot that in the other equation. Over c squared. That's a big deal because remember E equals mc squared. So to solve for mass, what is mass? Well, divide by c squared. Mass is the mass that's taken away by binding energy will be, sometimes they call that delta M equals binding energy over c squared. Sometimes this is referred to as a mass deficit. I might use that term at some point. This is the difference in mass caused by the fact that they're together. When there was that clap, there was that reduction in energy that lowers the mass by some delta M, which is the binding energy over c squared. Boom. Hope that makes sense. So that's our formula. Great. This one's easy. There's only one, right? This is one. We know this. This is one. There's one proton, one neutron. We know the binding energy. We got it all. So what's the mass? The mass is going to be 1.67262 times 10 to the negative 27 plus 1.67492 times 10 to the negative 27 plus, what's negative 3.564 negative 3.564 times 10 to the negative 13, let me get that exponent right, over 9 times 10 to the 16, which is c squared. C squared is always 9 times 10 to the 16. Great. If you do that, you get 3.34358, I'll round to that, times 10 to the negative 27 kilograms. Now, maybe it's more informative, and that's the mass of deuterium. You look it up. That's the number you get. It's a little bit less than the proton or neutron on their own by this amount. So this is the mass deficit. Delta M on its own, it might be fun to find, which I believe you get 3.96 times 10 to the negative 30 kilograms. What does this mean? This means that together, energy was released in their formation, or it takes energy input to pull those wave functions apart. It takes energy input to take them apart. And that energy you can think of as mass. It takes this much energy to pull them apart, or this much energy was released during their formation. Those are two ways of saying the same thing, which means that they lost this amount of mass during their formation, or you have to add this amount of mass energy to separate the proton and neutron into separate wave functions again. Is that kind of cool? I think it's kind of cool, right? It's a new way of looking at existence, but the whole point is like, this is the beginning of hydrogen fusion. This is the beginning of nuclear physics, is understanding that when nuclei are together, they have less mass due to the binding energy. Binding energy takes away mass. In class, I'm going to ask you guys if you want this to be positive or negative. I'm doing this video before class. That's it. Ask your questions. It's cool. The universe is here for us to discover. Thank you, friends.